So good morning, everyone. My name is SungBin Lee, and I'm the session chair. And the first talk of this day today is Professor Momoi from RIKEN, and he's going to talk about the supersolid in Kagome antiferromagnet. So let's welcome him.
Thank you. Good morning. I'm Tsutomu Momoi. I'm from RIKEN. So today I'm going to talk about supersolid in the Kagome antiferromagnet. And first of all, I would like to thank the organizers for giving me this opportunity. And this work was mainly done by Xavier Pratt. He's a postdoc in RIKEN. And also we worked with Chisa Hotta in University of Tokyo. So actually, she was also invited to this workshop, but unfortunately, she could not come because of her family reasons. But she said she wanted to come here. Okay, so I'll discuss spin structure in the Kagome antiferromagnet in a magnetic field. So we already know there are many magnetization plateau structure in this system. So here I want to discuss the spin structure in the non-plateau phases. And I mainly discuss about 5/9 plateau, instability in this 5/9 plateau, and try to discuss spin structure below this phase. And this work was already published in this paper. Okay, so let me start from the introduction. I'll discuss this usual Kagome antiferromagnet in applied magnetic field. And this system has flat band structure in many places. It is well known. For example, in classical limit, we know this system has massively degenerate ground state at zero field or in applied magnetic field. And this can be easily understood if we simply Fourier transform this Hamiltonian into this form. Then I just Fourier transform this Hamiltonian. Then we have this coupling constant in momentum space. Then this has this kind of flat mode in the lowest energy level. So actually this flat mode, appearance of this flat mode give this massively degenerate ground state. It is easily understood because there is a flat mode at the lowest level. Then we have a massively degenerate ground state in the classical limit. And this similar flat band structure appear in many places, even in quantum Kagome lattice. And I mainly discuss S equal 1/2 spin system. Then here, I'm considering magnon excitation at saturation field. We are considering system in strong magnetic field, so ground state is fully polarized. In that case, magnetic excitation can be simply obtained by simple flipped spin, and we can easily calculate the excitation energy of this magnon excitation. Then we again obtain this kind of band structure. And here we again have a flat mode at the lowest energy level. So in this case, flat mode corresponds to magnons are localized. So actually in real space, we can explicitly write down the wave function of this lowest energy excitation. Here, magnons are completely localized in a single hexagon. And if we look at the wave function of this localized magnon carefully, this wave function is oscillating like this one, plus minus, plus minus. So because of this oscillation, if we consider hopping amplitude to the other, these connecting spins, then all hopping amplitudes are cancelled because of this plus minus oscillation. So this is the reason why this magnon excitation is localized and it gives a flat mode here. But I want to discuss the other part of this magnon excitation today. So here we have these dispersive modes. And this comes from itinerant magnons in this system. And actually at saturation field, these itinerant magnons have always higher energy than the localized magnon. But I will come back to this structure later. This existence of these two types of magnons are important for this system. And existence of this localized magnon remind me Shastry-Sutherland material. So this Shastry-Sutherland lattice was already appeared in the previous talk, in the yesterday's talk. So it has a orthogonal dimers, and all lattice was covered with orthogonal dimers, and it has a, if we consider Heisenberg model on the Shastry-Sutherland lattice, ground state at zero field is an exact dimer state, and it has a finite energy gap above it. So in that case, it is known that this one magnon excited state, it's a tripron excited state, is nearly localized in this system. So this is a theoretical result, and also there is a closely relating material, strontium kappa-2 borate. So this system, in this system, kappa spin of 1/2, basically 1/2 spins form Shastry-Sutherland lattice. And in this case, this system was also studied experimentally very well. And this is a numerical, neutron scattering data for the strontium kappa-2 borate at zero field. And you see there is a many magnetic excitation, but the lowest energy state is nearly localized. It has an almost flat mode. So it is consistent with theoretical calculation. And if magnons are nearly localized, it means kinetic energy, effective kinetic energy is very small. So in comparison with interaction, if effective kinetic energy is very small, that means system is in the strong coupling region. So because system is in the strong coupling region, repulsive interaction between magnons become very important in this system, and it gives many magnetization plateaus in this system. So this is an experimental result for strontium kappa-2 borate. So there are several magnetization plateaus, and this is all data that now 1/3 plateau was also observed in the system. And this appearance of magnetization plateau can be easily understood by the crystallization of tripron excitations. And here is a theoretical calculation. So in theoretical calculation, if we consider tripron excitation as a particle, we can easily understand appearance of many magnetization plateau structure by taking account of repulsive interaction between tripron excitation, and then this repulsive interaction makes this kind of crystal structure stabilize, and it gives many plateau structure in this system. So for example, this 1/3 plateau is given by this stripe structure of tripron excitations. And also, in the vicinity of magnetization plateau, there appear supersolid structure. So here, it was first predicted from the theoretical calculation. And here, in the vicinity of magnetization plateau, there appear supersolid structure. So it means it's a coexistence of crystal structure of triprons and also superfluid component of tripron excitation. So in the spin language, it means it's a coexistence of spin density wave and also transverse spin long range order. So this was predicted by theory, but recently, not recently, but it was already partially experimentally observed. There is a certain evidence of from the experimental result. So this is a phase diagram given by experiments for strontium kappa-2 borate. And here is 1s plateau. This is magnetic field, and this is temperature, and here is 1s plateau, 1/8 plateau. So, but here width is very narrow. And at this field, this corresponds to this one. So this is an NMR spectrum of this system. And at this field, there is a certain structure in the internal field. So that means there is a crystal structure in this system. But if we increase magnetic field to this one, this magnetic field is already out of the plateau phase. So it's already in this non-plateau region. But still in this region, this internal shape of the NMR spectra has almost same structure as a previous plateau phase. So in this case, crystallized magnons are still exist in this phase, and extra magnons are moving around. It gives a long-range order in the transverse component. But because density of these extra magnons are very small in this case, so it doesn't change the shape of this NMR spectra a lot. So we think this is a partial evidence for the supersolid structure in this region. And also there is a result from the specific heat data. It corresponds to these open circles. And there is a very strong diverging peaks in the specific heat data here. So again, it means that certain discrete symmetry is broken in this phase. Okay, so this was a result in the Shastry-Sutherland lattice. And I want to say, so here, so the character of the almost localized magnon is important to induce this supersolid structure, because in several spin systems, supersolid structure was already numerically observed in various systems, but in many cases, they appeared only in strong Ising anisotropic case. But here, system is in the Heisenberg isotropic case. So in that case, this almost localized magnon is important to stabilize this supersolid structure. Okay, so I want to come back to the physics of Kagome antiferromagnet. So in this case, as I said, there is a nearly localized magnon in this system. So actually, it gives many plateau structure. These are numerical results for Kagome antiferromagnet in magnetic field. This is a magnetization process in applied field. So you see there are many plateau structures, 7/9, 5/9, and 1/3. And also there is one more small one here. And this result is given by DMRG calculation. And also there is a result from the exact diagonalization for this system. And at a certain value of magnetization, there appear threefold nearly degenerate low-lying state in the system. And above these threefold degenerate low-lying state, there are here, this is big spin gap here. So that means discrete, a sort of D3 symmetry is broken in these magnetizations. And because it is crystallized, it's a crystal, so it is stable state, and they open a gap, big gap above it. Okay, so, and okay, they also studied this magnetization plateau state carefully, and it is already shown that this plateau state has this crystal structure of spin density wave. This is a schematic picture of this plateau state. So here, on this hexagon with dashed circle, here, so, okay, so here, all Kagome lattice is decoupled into hexagons, and also spins connecting these hexagons. So we decouple it into the two sublattices, A sublattice and also B sublattice. And on A sublattice, if we consider lowest energy state in the total SZ equal N sector, and also if we consider spin on B sublattice a fully polarized state, and this product state gives a very accurate state, ground state for this magnetization plateau state. This was shown by the numerical calculation, and when this number of the total magnetization n, this n is an integer number, and when this n is 0, 0 corresponds to the case when total magnetization is 1/3. Ratio of the total magnetization is 1/3, and n equal 1 corresponds to 5/9, and n equal 2 corresponds to 7/9. Okay, so this was already known. So my question is, okay, so if we change the magnetization from this fractional value, then what happened to this system? It is known. It's not known yet. But partially, there is a certain evidence of supersolid in the result from the exact diagonalization calculation. So here, red circle corresponds to plateau state. There is a 3-4 degenerate state. But if we slightly decrease the magnetization by 1 or here by 2, then there still exists this nearly degenerate 3-4 degenerate state in the lowest energy level. So that means even if magnetization is not a fractional value, but still there appear similar spin density wave crystal structure in this phase. So this indicates the appearance of supersolid in this system. Okay, so this is our motivation, and we study this system using degenerate perturbation theory. Because as I said, spin density wave magnetization proto state can be well described with product state previously I mentioned. So I started from this product state and performed perturbational expansion. This is just a usual conventional perturbational expansion and try to estimate what is the instability to destabilize this plateau state. So here we consider this crystallized hexamerized Kagome lattice. We decouple Kagome lattice into hexagon and other connecting spins. So hexagon rings on the hexagon have coupling J, and rings on these connecting spins have coupling J prime. And good point for considering this lattice is this lattice has the same space symmetry as the plateau states. And also in the J prime equals 0 limit, we can easily obtain the exact ground state for this state. And this is a magnetization process for this system. And you see there are many plateaus, which is exactly same as the previous Kagome lattice plateaus, 7/9 and 5/9 and 1/3. And also good point is ground state of these plateau states are exactly given by the previous product state. So that means previous product state is a good starting point for studying this model. And we can safely perform perturbation expansion starting from this product state and use this J prime interaction as a perturbation. So because there is a big spin gap above this ground state, perturbation expansion is very stable, and it's a safe approach to study this problem. And actually, we perform degenerate perturbation up to 3rd order. This is not easy calculation, but Xavier Pratt did this calculation. Okay, so here is a degenerate basis in case we decrease total magnetization by 1. So in that case, we are considering a sort of downspin in the system. So, but here we started from this product state. So one possible excited state is just decrease total magnetization in a 1 hexagon by 1. So in usual hexagon, total magnetization is given by n, but only here, total magnetization is n equal n minus 1. And another type of local excitation is given by this downspin on connecting spins. So there are these two types of excitation. But here on hexagon, it has 6 spins, so that means there are many energy levels. So we consider these levels separately. Okay, so this is the result of our calculation. Here we are considering this 5/9 plateau. So as I said, in the J prime equals 0 limit, it shows us very stable plateau, and perturbation is very stable against this state. So by applying perturbation, this state is continuously changed by perturbation, and we show that even if J prime equal 1, this plateau is still stable here. So I will show our result here. So first, we consider lowest energy magnon in hexagon. As I said, there are many levels in the magnon. So first, I consider lowest energy magnon in hexagon, but this state is localized. The reason is quite similar to the previous localized magnon at the saturation field. At that time, there's a plus-minus oscillation cancels the hopping amplitude. So this mechanism is quite similar. Again, here, certain symmetry of this localized magnon cancels all hopping amplitude. So again, there appear flat mode. So if this gives a instability, it doesn't give interesting physics. It just shows magnetization jump. So it's not very interesting. But if we consider second energy level in the hexagon, it can move around. For example, it's simply, there's a direct hopping between connecting spin and this second energy level of the hexagon. So it can move around by simple perturbation. So because it gains kinetic energy, hopping amplitude, dispersion, energy dispersion, it has an energy dispersion. So, and good point is because it gains kinetic energy, sometimes this dispersive mode has lower energy than the previous localized flat mode. Okay, sorry, this is a very technical page, so you don't need to seriously read. I just want to show we perform calculation very seriously. So here, this is the effective Hamiltonian for the itinerant magnon in the second energy level of hexagon. So it can, from the perturbation, we have many hopping amplitude. For example, there's a hopping amplitude between nearest neighbor hexagon. This big circle means hexagon sites, and small circle means connecting spins. So there's a hopping amplitude between hexagon and connecting spins, and also between connecting spins. So originally, there was no interaction between connecting spins, but because the appearance of this crystal structure, there appear certain energy separation in the system, and we consider only low energy sector. In the low energy sector, we obtain this kind of effective hopping amplitude between these connecting spins. Some of them are long-range interaction. But among them, we evaluated the value of this coupling, and here, two of them are dominant in this case. So one is a nearest neighbor hopping amplitude between hexagon and connected spin, and the other one is a hopping amplitude between second neighbor connecting spins. So again, this second neighbor connecting spin form big Kagome lattice. So actually, there are three big Kagome planes here. So again, it contains many fluctuations in this effective Hamiltonian. And here is a magnon instability. We calculated the lowest energy state, changing the J prime. So when J prime is very small, still flat mode gives the lowest energy state. So it doesn't give any interesting physics. It just shows magnetization jump. But when J prime becomes strong, it is comparable with J. So this one corresponds to uniform Kagome lattice. So around here, we found this dispersive mode gain kinetic energy, and it has lower energy than the flat mode. This red dashed line corresponds to localized flat mode, but now dispersive mode has lower energy than the flat mode. So here, itinerant magnon can give instability to this system. And in case of Kagome lattice, this gamma point instability has the lowest energy, and it has twofold degeneracy here. And I want to talk about this twofold degeneracy more. So this is a dispersion for magnon excitation, and because it has a gamma point wave vector, so that means this is uniform in the deformed Kagome lattice. But in the unit cell of the crystallized Kagome lattice, there is a one hexagon site and also three connecting spins. So even if this is gamma point wave vector, it still can have a three sublattice structure. So if we write down these three sublattices separately, we can write this. We can obtain the wave function of this lowest energy state, and we can analyze this wave function decoupling these three sublattices, and it has these two forms. So one is this one, and the other one is obtained simply applying complex conjugate to the previous one. So this relation, this form of magnon state is quite similar to the magnon instability in the triangular lattice antiferromagnet at saturation field. In that case, in the triangular antiferromagnet at saturation field, so magnon instability has a wave vector at the corner of the brilliant zone, Q. But in that case, there are 2 points, Q and minus Q. So sometimes these two states, two instability can induce various spin configuration below saturation field. For example, if one of Q is selected, we can obtain this kind of umbrella state. It's a conical state. But if two of them are degenerated with same density, then we have this kind of coplanar state. One is a plateau V state, and the other one is a psi state, like this one. Both of them are coplanar state. These are obtained. These are in the double Q states. So in our situation, in our case, in our model, we again can have a similar physics because these two instability have exactly the same form as a triangular lattice system. So that means these three sublattices on connected spin can again have this spin configuration below the lower boundary of the plateau state. Okay, so it is, in case of triangular lattice antiferromagnet, it is known that anisotropy of the Hamiltonian, anisotropy of a spin exchange determine which state is selected here. So to determine which one is selected in Kagome lattice, we need to know the interaction between magnons. So here we studied interaction between magnons, and we considered all possible two magnon scattering process in this system. So there are, again, many interactions, but there are three types. One is a simple repulsive interaction, and the other one is this correlated hopping process, and the last one is a magnon pair hopping process. And we evaluated all coupling, and we found two of them again have a dominant value, and these are both simple repulsive interaction, and they exist on the same links as a previously mentioned dominant hopping amplitude. So here there is a repulsive interaction between hexagon and nearest neighbor connecting spin sites, and also there is simple repulsive interaction between second neighbor connecting spins here. These are dominant repulsive interaction. Okay, so to analyze, we are using a sort of dilute Bose-gas approach to study the spin structure below the plateau. So in that case, repulsive interaction, we found there is a strong repulsive interaction. So this repulsive interaction is very important to stabilize dilute Bose-gas. Because there is repulsive interaction, it cannot show phase separation. So it can be a stable dilute Bose-gas. It's a dilute magnon gas. So it means this transition, this is a magnetization process, this transition from plateau to non-plateau state can be a continuous transition. And also, if we compare the energy of the critical field determined from our calculation, it gives this lower boundary is 2.3 or something. But this is quite consistent with the numerically obtained value estimated from the DMRG calculation. So we think this transition can be well described with our magnon instability. So this is important information that this transition is a continuous. So continuous means here is a crystal structure in plateau state. This crystal structure still remains in this non-plateau phase. As as I said, we obtain repulsive interaction and also hopping amplitude. But if we compare two values, this repulsive interaction is stronger than the hopping amplitude. So that means system is still in the strong coupling regime. So in this case, this Ising anisotropy, if we consider effective spin interaction between these connecting spins, this effective interaction has strong Ising anisotropy. So in that case, again, we can obtain the spin structure below this plateau state, and we found this Ising anisotropy select this coplanar V states among these three possible states. And here we performed B field approximation. We already have an effective Hamiltonian for the interacting magnons. So here we applied mean field approximation to this system, and we obtain this type of coplanar V state appear in this non-planar, non-plateau states. Here is a crystallized hexagon site, and these are connecting spins around this hexagon. So they have three sublattice structure, and two of they are slightly canted gradually at here and canted a lot, and this total magnetization decrease gradually to here. Then in this approach, we enter into this phase from this transition point. So this transition becomes first order in this approach. But we need to study this instability in this one-third plateau, because there is another instability here. There can be another instability here. So this might explain the phase above this phase. So we need to study the instability here. And we also study various plateau states, and we perform similar calculation to this phase. For example, this is the upper boundary of the one-third plateau phase, but in this case, our calculation doesn't work. Doesn't work is not good word, but we can say single magnon instability cannot explain this transition, because it is partially because if we consider perturbation by increasing the magnetization by 1, then we can only consider local bases like this one. Here, hexagon site has magnetization in the hexagon site is increased by 1. But connecting spins are already fully polarized, so this spin cannot be flipped, or magnon excitation cannot exist on this hexagon site. So excitation can exist only on hexagon, but in this case, there's no simple exchange process between this site and this up spins, because this is already up spin, so we cannot move this up, a sort of up spin to this side. So it's not easy in this case. This magnon excitation cannot move easily in this case. So in many cases in this system here, if we consider upper boundary of the plateau, almost localized magnon gives instability to the system. But in this case, the value estimated from this localized magnon, the value of lower boundary estimated from this localized magnon is quite different from the numerically obtained value. In numerical calculation, this one-third plateau destabilizes much lower field. So that means there is another type of instability in the system. Or it can be a simple first-order phase transition. It jumps into completely different structure. So we cannot study this transition with an instability argument. So first-order phase transition is one possibility, and the other one is a more exotic magnetic excitation. We don't really know. So we can only say single magnon instability cannot explain the transition between this line, between these phases. And also here, again, we have a localized magnon here in the upper boundary of this 5/9 plateau. But in this case, the value of the upper boundary is almost same as the numerically obtained results. And actually, so if localized magnon is gives an instability to the system. It shows a magnetization jump. So it seems that this result is consistent with this numerical calculation. In numerical calculation, here is a sort of jump structure, or slope is very steep here. So we think this localized or nearly localized magnon might be consistent with a numerical calculation. And another point is here we have a 7/9 plateau, but at the lower boundary of this phase, we have this transition point. But in this case, our calculation doesn't converge well. So we are performing perturbational expansion. So in that case, this perturbation series need to be converged well. But here, this convergence is not good. So unfortunately, we cannot say meaningful result here. So these are all of our results. And this is a summary of my talk. So we calculated stability of magnetization plateaus in Kagome antiferromagnet. So they are quite stable at the J prime equals 0 limit. But we found that they still, for example, in case of 5/9 plateau, it is still stable even in the Kagome limit. And at the lower boundary of this phase, this transition can be continuous. And below this line, there still exists crystal structure, the same as the plateau states. And also there is a coexistence of this crystal structure and also superfluid component of magnon excitation. And it gives this kind of coplanar V state here. So that's all my talk. Thank you for your attention.
Thank you for your talk. Any questions?
Hello. So I was just curious about, you mentioned in the numerical data there is a threefold degeneracy in the Caponi et al. Data, right? Mm-hmm. But when you do the hexamerization, there's only one ground state. So how do you, when you go to J prime equals 1, do you recover that threefold degeneracy, or what happens exactly?
Oh, so, okay, so right, so when J prime is smaller than 1, there's no degeneracy. But by changing the lattice structure, we think other two states come down to the ground state threefold degeneracy in the Kagome lattice. So we chose one of them by the lattice structure and study the stability in this one of the ground state. Because it's a symmetry broken state, so we can choose one of them.
Any other question? If not, let's thank Professor Momoi again.